So today I'm going to be discussing viewing preferences for motion and depth in stereoscopic 3D film. So first, as I'm sure many of you are aware, within 2D film, if your filming practices are not optimized and you add motion to that film, you're going to introduce the possibility of motion artifacts, so things like motion judder and motion blur, which I've illustrated here. But within 2D film, we have these well-established rules of thumb where we know we can adjust a few parameters, such as focal length, shutter angle, and frame rate, and reduce these distortions in our final product. However, when we try to apply these rules to three-dimensional film, we run into the problem with the addition of binocular parallax. So when we're adding this new highly salient cue to depth to an already natural scene, we're going to run the risk of mismatching this new depth cue with the already two-dimensional depth cues that exist within that natural scene. And this is, of course, what can lead to incomplete, ambiguous, or contradictory percepts in your final product. So between the distortions from the mismatch of depth cues within 3D film, combined with the distortions we know can come from the addition of motion, applying these rules of thumb to 3D film can get very complex. So, our most immediate solution to this problem is to very precisely allocate our depth budget when it comes to creating stereoscopic 3D content. However, the absence of general guidelines for the optimal creation of stereoscopic 3D film has left great debate in the literature surrounding what parameters are actually critical to creating the ideal viewing experience. And if we actually go back into that literature and look at different assessments of viewing experience, we can see the vast majority of these studies focus on factors that affect viewer comfort. So within these studies of viewer comfort, the general focus is on subjective measures of comfort. So using something like a rating scale or a questionnaire to directly assess how comfortable viewers find a particular sequence. And I'm sure we're all looking forward to all the viewer comfort talks that precede my current talk. So with the general consensus within this literature is that we tend to get lower ratings of comfort in scenes that have either changes in binocular parallax or very excessive binocular parallax, or in scenes with high amounts of motion or very rapid motion. Now, it's very important for us to understand how people respond to stereoscopic 3D content. However, within this literature, there's one dimension that has yet to be explored, and that is how these two factors affect a measure of viewer preferences. So within this current study, I set out to evaluate viewers' aesthetic preferences for camera motion within stereoscopic 3D sequences in a theater viewing environment. And it was very important to do it within a theater viewing environment, not only to keep it similar to how people traditionally view 3D films, but we wanted to free ourselves from a lot of restrictions that come with experimental testing conditions such as reduced viewing distances. So because no previous study has actually assessed how these factors affect viewer comfort, we've actually based our previous predictions on measures of viewer comfort. So what we might predict is that we should see stronger preferences for slower camera speeds and depth and smaller interaxial distances. So for our current study, the stimuli that we actually use for filming can be seen on the right here. So we had a professional actor perform a 6-second dance phrase, and this dance phrase was filmed under a variety of different parameters. So here we have our two main parameters of interest, the effect of motion and the effect of binocular parallax. So for motion, we actually split it into two different components. So first, we had the direction of that motion. So we had two different conditions, the first being a z-axis motion condition. So this was a dolly shot towards the actor in depth, whereas our lateral motion condition was a tracking shot from the left side of the set to the right side of the set as the focus remained on our actor in the center. And of course, the second component of this motion was the speed of that motion. So we had three different conditions of low, medium, and high speed, which correspond to these speeds below in meters per second. And this is the speed of the camera along our dolly and track system. And of course, for binocular parallax, we manipulated the interaxial distance between our two cameras, so we had a 0, small, and large IA condition, which correspond to 0, 10, and 65 millimeters respectively. So this dance phrase was filmed under every combination of these parameters. So what we ended up with was 18 unique video clips, or 9 unique video clips for each direction of motion. And actually right now I have a couple examples of the stimuli that we used during our experiment, so if you can put on your polarized glasses. And if we can get the clips up. Good, great. So what you're going to be seeing is the first two clips are an example of our z-axis motion condition. So you'll see the fastest and the slowest speeds in that condition, followed by our two lateral motion conditions. And just as you're viewing those, I just want you to be aware that we did have other objects in the scene besides just our actor in the middle. So we did have two other students seated different distances away from the camera, as well as these panels that were situated behind the actor to act as a very fixed reference for our background. So we did have lots of other relative depth cues. And I believe that's just the 4 clips I brought. They're very short, as each one is only 6 seconds long. Okay, so for our testing sessions, we actually split our observers into 2 different groups based on the motion direction for that condition. So when an observer came into a testing session, they were assigned to either the z-axis motion or the lateral motion condition, depending on what we were testing that day. And then within each of those conditions, viewers would view pairs of video clips, each with a different combination of our 3 levels of speed and our 3 levels of IA. So within a testing session, in a particular trial, observers would be presented with 2 video clips presented sequentially, and the task we actually asked of our observers was, which clip did you prefer, the first one that was presented or the second one that was presented? And observers gave their responses using electronic remotes, which not only greatly cut down on our test time, but also reduced coding errors within our data collection. So first, what I'll show you is our effect of interaxial distance. So here, what you're seeing is along the y-axis, we had the proportion of responses. What this is the number of times each observer chose a particular video clip over the total number of times that was presented for a testing session. So the greater this number, the greater the preference for that particular condition. And of course, this was averaged across all our observers. And here I have our 3 levels of interaxial distance along the x-axis. So what you can clearly see from this graph is there's actually no effect of interaxial distance, and even if you compare our 2D condition, so our 0 IA condition to our 2 3D conditions, there's no significant difference between those 2 conditions. So what we actually see in these, under these circumstances, the presence or absence of stereoscopic 3D does not actually affect viewer preferences in this case. However, if we look at the effect of camera motion, we do see a significant effect. So again, here I have the proportion of responses on the y-axis and our 3 levels of camera speed along the x-axis. So first, if we look at our z-axis motion condition, you can see there is this positive increasing trend as camera speed increases along the z-axis, and this effect is actually significant according to our statistical analysis. However, if we look at this lateral condition, we see a flat, slightly decreasing trend as camera speed increases, and this effect is actually not significant. So there is no significant effect of camera speed in the lateral motion condition. So what this actually suggests is that within our study, viewer preferences only seems to be affected by camera speed when that motion is along the z-axis. And specifically what we see is that we get stronger preferences for fast camera speeds along the z-axis. Now, this result is actually quite interesting given our previous predictions based on viewer comfort. So just to recap what I stated earlier about the general consensus of viewer comfort literature is that you tend to get higher ratings of comfort in scenes with either low amounts of motion or small amounts of binocular parallax. So based on that criteria, we would predict for our z-axis motion condition that we should see lower preferences for our 3D conditions compared to our 2D conditions, as well as lower preferences for fast camera speeds. However, in our current study where we assessed a measure of viewer preferences, we're seeing strong preferences for fast motion along the z-axis and no effect of binocular parallax. So now we effectively have to ask ourselves, why are we getting these differential results when we based our predictions on previous literature of viewer comfort? Now, one possibility might be that the factors that should have maximized viewer comfort in this case do not necessarily produce maximum enjoyment within the viewer. That perhaps under these conditions, Preferences for faster motion may have been driven by other factors. And now we essentially have to ask ourselves what is present within the z-axis motion condition that's not present in the lateral motion condition that could be driving this result of preferences that we see. And one possibility might be the presence of looming cues. So looming cues simply refer to the increase in size of an image on the retina that's caused by an approaching object. I'm sure many of you have experienced this probably every day, but as objects get closer to you, they not only appear perceptually larger, but that change in size also corresponds to that change in size on your retina. And there's been many studies that have shown humans can use these cues to very precisely estimate the time of collision of objects. And one very classic example is the throwing and catching of a baseball. And of course, the higher the velocity of those objects, the much more imminent that collision is going to be, and the much more salient that information is going to be to an observer. Now, one thing that's actually unique about looming cues is because they're defined by that change in size of the retinal image, they're actually a monocular cue. That is, they only depend on the information from one eye. So, if the presence of these looming cues were somehow driving the effect of preference that we see, we would not expect there to be an effect of interaxial distance because it is a monocular cue. So now we have to ask ourselves, why is there an effect of speed in motion along the z-axis? So the first possible factor of why we get this effect of speed I sort of alluded to in my previous slide, but it might be due to the differences in object motion alone between the two conditions. So because our z-axis motion does have the presence of these looming cues, it might be the fact that the higher the velocity of that moving object, the more salient that information is, and it's possible that this effect of speed within looming cues may have been enough to produce the effect of camera speed that we see in the current study. However, one thing that's also unique about an object moving in depth is that it also has changes in depth information or disparity information. And one thing we actually did not see in our study is we did not see a difference between our 2D and our 3D conditions. So if observers were using the object motion alone to base their judgments of preference, we would probably expect to see a difference between our 2D and our 3D conditions, since our 3D conditions would have this change in disparity information as interaxial distance increased, but our 2D condition does not have this change in disparity information. So it's likely that this could be a contributing factor to the preference results we see, but it's likely not the only factor driving the results. So another possibility may be an effect of linear vection. So when I say vection, I'm referring to the illusionary self-motion that a stationary observer feels when a large portion of their visual field moves. And a very classic example is a observer sitting on a stationary train as another train passes by them. And as they stare out the window at this train moving by, eventually they might get the sensation that they themselves are moving even though they are stationary. And there have been a few studies that has shown that in displays of the same size, you can get situations where looming optic flow can produce a greater sense of vection than lateral optic flow. However, it has been shown that these studies have been situationally dependent. But given our experimental setup and the stimuli used in our experiment, this is still a possible explanation for our results. So our observers could have been responding to an increased sensation of vection as speed increased along the z-axis. And lastly, because we're dealing with something as subjective as preference, we can't ignore the possibility of higher order cognitive effects. So one possibility might have been our observers were responding to a greater sense of immersion in camera motion along the z-axis. So one thing that is different between these two conditions is the direction of the movement between the z-axis condition and the lateral motion condition. So that movement, that dolly shot towards the actor in depth, is indicative of entering that scene, whereas in the lateral motion, that left-right movement is more indicative of passing by that scene. And it might have been possible that as camera speed increased along the z-axis and that movement into the scene also increased, we might have gotten an increased sense of engagement and therefore a greater sense of immersion in those conditions. However, it's important to point out that within this current study, we actually do not have a direct measure of object motion, linear vection, or immersion, but given our stimulus and our experimental setup, these are viable factors that could have contributed to the preference results that I've reported here, and these are by no means the only factors that could have been contributed to the results I've reported here. So what can we conclude based on the results of this current study? One thing I've clearly shown is that viewer preferences for moving stereoscopic 3D content do not necessarily depend on the same factors that influence visual comfort, that in fact, in this case, a variable can influence visual comfort and viewer preferences in very different ways, which I've shown here through the effects of motion and binocular parallax, but there could also be other variables that we did not control for within this current study. So in some situations, enhancing comfort may produce less appealing content to the viewers. And of course, as filmmakers, we really need to be aware of this balance between comfort and preference in stereoscopic 3D content in order to produce both an enjoyable and a comfortable viewing experience. And just before I complete my talk, I just want to thank not only our funding agencies for this project, but also my 4 lovely co-authors. Thank you.